Hello friends, welcome back to the IARE YouTube channel. Today, I would like to discuss one of the scheduling algorithm, which is shortest job first scheduling algorithm. So, today we are going to discuss one of the process scheduling algorithm, shortest job first scheduling in today's session. So, with this session, the student able to understand various CPU scheduling algorithms, and he will also understand what are the evaluation criteria for selecting the CPU scheduling algorithm for a particular system. These are the two different outcomes the student able to carry out after end of this presentation. So now let us move to the concept. So the shortest job first scheduling algorithm. The name itself has given a small minimum meaning, shortest job first, right? In previous session, we have learned one scheduling algorithm, that is first come first serve scheduling algorithm. Today, we are going to discuss shortest job first scheduling algorithm, and the name has the means that in this scheduling algorithm, the scheduler will pick the process which is having the shortest CPU burst time, which is having the smallest CPU burst time. That process will be picked from the ready queue, right? So, this algorithm associated with each process the length of the process next CPU burst. Each process, the length of the process next CPU burst means that, so when the process are sitting in a ready queue to acquire the CPU, so here the scheduler will pick the process based on the scheduling algorithm. So if the scheduling algorithm is the shortest job first, then that scheduler will pick a process which is having the smallest burst time will get the CPU, right? So that's the reason, that means that a process scheduling, that scheduler will pick the process of smallest time, smallest CPU burst time, process will get the CPU. So it is also called shortest job next scheduling, because so the scheduling depend on the process next CPU burst. That's why this algorithm we also call it as shortest job next scheduling. Shortest job next scheduling, because scheduling will be based on the CPU's burst time of the next process, right? So whenever the CPU is available, then it will be assigned to the process that the smallest next CPU burst. Okay. If you have two processes are having the same CPU burst, same next CPU burst, then at that time, who will get the processor? Who will get the CPU? Means that time it will apply first come first serve scheduling algorithm. If two processes are the same, then FCFS scheduling is used to break the time. Whoever comes first, that process will get the processor. So this shortest job first scheduling either be preemptive or non-preemptive. Either preemptive or non-preemptive. Preemptive means that you can allow the CPU to other process. So some other higher priority process comes, some interrupt comes. So that time CPU will be switched from one process to other process. So that's nothing but preemptive. So in non-preemptive mode, so you are unable to take away the CPU. Okay? Unable to take away. Forcibly you are not able to take away the CPU from a process. Process can voluntarily give. That is allowed. That is nothing but non-preemptive mode. This also we have discussed in the previous sessions. So what are the different types of the shortest job first scheduling? As we discussed, this scheduling algorithm available in non-preemptive mode and preemptive mode. Under non-preemptive mode, another name for the SJF, shortest job next scheduling. Some textbooks will use the shortest job next scheduling algorithm. And in the preemptive mode, this same shortest job first algorithm will also call it as shortest remaining time first. Shortest remaining time first algorithm. Right? So let me see what are the different problems we will solve with the help of SJF algorithm. So let us see SJF under non-preemptive mode. We will see one example. So if the question is, consider the following set of processes with length of CPU burst given in milliseconds. So here how many processes are there? 4 processes are there. So what is the burst time of the 4 processes? So P1 is having 6, P2 is having 8, P3 is having 7 and P4 is having 3 milliseconds of the burst time. Burst time is nothing but execution time of a process. Execution time of the process is in the sense of that a process will take the CPU for the execution of an instruction, will use the CPU, right? So here the question, if the CPU scheduling policy is SJF, non-preemptive, then calculate the average waiting time and average turnaround time, right? If the question comes like this, how we will solve this problem? So once first enter into the problem, so we will have to draw the GNAT chart, because the GNAT chart will helpful. Pictorially we will represent which process are executed at particular moment, right? So here with this example, P1 6, P2 8, P3 7, P4 3 milliseconds. Now out of this all the process which is having of the smallest burst time, P4 is having the smallest burst time, right? Here in this problem, we are assuming the arrival time of the process. All processes are arrived at time interval 0. All processes are arrived at time interval 0. So means for all process arrival time is 0. We are considering, we are assuming for this problem because they haven't given the arrival time, means that all the processes are arrived at time 0. Now this is a burst time. So among this burst time, which process is having the smallest burst time? So here P4 is having the smallest. Then who will get the first chance of the CPU? P4 will acquire the CPU. So P4. So it is non-preemptive mode. So there is no preemption. Once P4 is acquired the CPU, then P4 will continue the execution and after completion it will release the CPU to another process. So here P4 is acquiring at 0 units, it arrived inside the system and it has taken the 3 units. So waiting time is 0, then completion time for the P4 is 3. Completion time for P4 is 3. Now let us see the question. So who is the next actually smallest time? Once actually P4 is completed. So who is the next smallest time? In this queue, 6. P1 is having the smallest burst time. So Now next, P1 is going to acquire the CPU. P1 will use the CPU for the execution. 3 plus at time interval 3 means that the P1 is waiting till 3 milliseconds to acquire the CPU. The waiting time for the P1 is 3. So 3 plus how much time actually it is using the CPU? 6. 3 plus 6, 9. Right? So now the P1 also completed. P1 also completed. Now who are in the ready queue? P2 and P3 are still in the ready queue, waiting to acquire the CPU. So out of this P2 and P3, who is having the smallest burst time? 7 is the smallest burst time. So now after P1 completion, who will get a chance to acquire the CPU? P3 will get a chance to acquire. So P3. So what is the burst time of the P3? P3 is 7. So means that 9 plus 7. It is 16. How much time actually P3 is waiting? P3 is waiting in a queue till 9 milliseconds. 9 milliseconds because P3 arrive at 0 and till 9 milliseconds P3 is waiting in the ready queue. So at time 9, P3 is take the CPU and complete the execution at 16 milliseconds. So the waiting time of P3 is 9. The completion time of the P3 is 6. So now who is left in this ready queue? Only P2 is left in the ready queue. P2 will take the remaining CPU time. And 16 plus 8. So it is going to be 24. The waiting time of the P2 is 16. The completion time of the P2 is 24. Now let us calculate what is actually in the question they have asked. Average, we have to calculate average waiting time and average turnaround time. We will see that how much actually we will get with this example. So what we already know the formulas, turnaround time is nothing but how we will calculate the turnaround time. The difference between time submission and time completion is nothing but turnaround time. Means that completion time minus arrival time. Completion time minus arrival time. For P1, let us calculate now turnaround time. P1, see here, the completion time is 9. So arrival time is 0. 9 minus 0 equal to 9. For P2, completion time is 24. 24 minus 0, 24. For P3, 16. For P3, 16. 16 minus arrival time, 0, equal to 16. So for P4, completion time is 3. 3 minus arrival time, 0, 3. That equal to 3. Now we have all the turnaround times for the all process P1, P2, P3, P4. Now let us see how to calculate average turnaround time. 9 plus 24 plus 16 plus 3 divided by the number of processes. So equal to 30 milliseconds. 30 milliseconds. Now let us recalculate the another parameter, waiting time. Because these parameters will decide the performance of a system, right? Whether it is interactive, whether it is actually what kind of the system, for what kind of the system this scheduling algorithm you have to apply also, we will come to know. So now let us see how to calculate the waiting time for each and every process. So now 4 processes are in a system. Waiting time for P1. You look at P1 when it is started executing. So till 3 units of the time, the P1 is waiting, right? So up to that point P4 is executed and P1 is waiting to get the CPU. So waiting time is 3, right? With this GNAT chart we can easily figure it out. What is the formula for waiting time? Turnaround time minus burst time. Turnaround time, what is the turnaround time? 9 minus 6. 9 minus 6, 3. So here also with this picture, both should be matched. Both should be matched. So even with the formula, even with help of NAT chart, so both values should be matched. Right? Now you got 3. So now let us see for P2. For P2, 16. The P2 has waited 16 milliseconds in a ready queue. Right? Let us see. Turnaround time of the P2. Turnaround time of the P2 is 24 minus burst time. Right? 8. 24 minus 8 equal to 16. So 16. This is matching. Right? Now look at the P3. P3 turnaround time 16 minus burst time. 16 minus burst time 7 equal to 9. So P3 waiting time is 9. So here for the similar way for P4 equal to also turnaround time 3, burst time is 3. 3 minus 3 equal to 0. So the waiting time for P4 also 0. Right? So always in the GNAT chart, if you observe here, the starting value gives the waiting time and the ending value will give the completion time. Right? In non-preemptive mode only. In non-preemptive mode. That is actually you have to remember. Because in non-preemptive mode only, actually CPU is not allowed to take by the some other process. Because it is not going to be preempted. Even the preemptive version, the CPU will be preempted once actually based on the scheduling algorithm, it will preempt and it will assign to some other process. So with this, what value we are getting? Average waiting time equal to 7 milliseconds. Average waiting time equal to 7. Because see, 3 plus 16 plus 9 plus 0 divided by the number of processes 4 equal to 7 milliseconds. So now the same example. So average waiting time equal to 7. Average turnaround time equal to 13 milliseconds. So if you calculate, if you apply the before already explained example algorithm of FCFS, first come first serve scheduling algorithm. So if you apply to the same problem, you are going to get average waiting time 10.25 milliseconds. I am not going to do again here the solution by applying FCFS to this problem. You just calculate because in the previous session I have done multiple problems. So the average waiting time is going to get 10.25 milliseconds. So what we got it with the SJF 7 milliseconds. So are we have any improvement in SJF or not? So it means we have an improvement in SJF scheduling algorithm. Now with this we can say SJF is optimal because it gives the minimum average waiting time for a given set of processes. So what is the main difficulty with this SJF? To apply this SJF scheduling, okay, SJF is a good algorithm and it is giving optimal values. So what is actually the difficulty? Is it practically feasible? Is it practically implementable? So it means that practically SJF is not possible. Why? Means that, so we have to predict, we have to know the next CPU burst time for a process is very difficult. So because everybody know, right? So how can we assume priorly itself this much time the CPU will be taken away by this process? So right, that prediction, that assumption is very difficult. So for that sake, SJF is theoretically we can apply, but practically it is not possible. Practically it is not feasible to apply this. Then why actually this scheduling algorithm is coming up? So means that some scenarios, if you know, if you observe that when we studied actually the initial different types of the systems. So in that we have batch systems, right? Batch systems means that the jobs are executed as a pool. So at that time, we come to know how much time actually the CPU requires to the process, to the job. So in that scenarios, so the SJF scheduling algorithm is the best algorithm and it will give the optimal results. Optimal results in the sense of that it will give the minimum average waiting time. Minimum average waiting time to the processes. Right? So for interactive systems means that the time sharing systems. So where the preemption is there. In those scenarios, the SJF is not practically possible. So in other words, SJF can't able to apply at the short-term scheduling phase. So we already know the process phase. So it is also one of the important bits. When we studied the process state diagram, ready to running, who will be decide short-term scheduler will be taken care. So this SJF is not possible to at the time of implement at the state of short-term scheduling. So it can able to apply long-term scheduling from new to ready state. From new to ready state if you remember of process states. And particularly let us we see the another example shortest job first scheduling where the process are arrived at different time intervals. Let us see this scenario of the example. Then we will move to the primitive version of the SJF. Right? So the question is, the considers a set of 5 processes whose arrival time and burst time are given below. And if the CPU scheduling policy is SJF in non-preemptive, in examinations also you should be more cautious what kind of mode they have given. Either preemptive version they have asked or non-preemptive version they have asked. So based on that, you have to try to solve the problem. So in this problem, we are solving using non-preemptive version. Calculate the average waiting time and average turnaround time. So for all the problems like that, we will apply the GNAT chart. So we will draw the GNAT chart for the problem. Because GNAT chart is a graphical representation all of the which process are executing or which process is taking the CPU and executing. Right? Now, let us see what are the different arrival times, what are the burst times. 3. Process 1 is having process 1 is arrived at 3. Process 1 burst time is 1 milliseconds. P2 is 1. P2 is arrived at 1, time interval 1, and burst time is 4, execution time, because it requires, P2 requires 4 milliseconds of the CPU. And P3 is arrived at 4 milliseconds and it requires CPUs of time 2 milliseconds. P4 is arrived at 0 and P4 is requires 6 milliseconds of the CPU time. P5 arrives at 2 and requires 3 milliseconds of the CPU time. So let us see at time 0 who are there in this entire of the at that moment. So at time 0 only P4 is coming. Right? P4 only one process is sitting in the ready queue. So how much time actually it requires? It requires 6. Right? So now who will get the first CPU? P4 will get the CPU. Even though now with SJF, please look at carefully. In SJF, we will look at the shortest burst time of the process. Right? At P4, because at time interval, here we need to consider the time interval. At what time actually, how many processes are in the system at present. Then we will look at the among of those processes, we will look at the shortest burst time. Right? So now here initially at time 0, so only one process, P4 is arrived. So P4 is taken. P4 is taken. So because it is non-preemptive version, so once P4 is acquiring the CPU, it will complete the execution. It will finish the execution till 6 units of the time. Now let us see. The next. So at time 1, because till the 6 units of the time. Now who are the processes are in the ready queue? So because all other remaining processes are coming to the picture. This is completed. This P4 is executed. So now who are in ready queue? P1, P2, P3. P2 is arrived at 1. Right? P1 is arrived at 3. P5 is arrived at 2. Now who are in ready queue? Because 5 units of the time is over. So by that time, who are all the processes are in the queue? P1, P2, P3 and P5. So among this, you have to look at which one is having the smallest burst time. Which one is having the smallest burst time? 1. So P1 will get the CPU. So P1, what is the burst time for P1? 6 plus 1. 1 millisecond. P1 will take the CPU and complete the execution. So 7. So now everyone is in the ready queue. Right? So now let us see P1 also completed. Now who are the process? Now the time is 7. Right? So by this 7, all the process. Now look at who is the actually next smallest burst time. Which process is having the smallest burst time? P3. Right? P3 is having the smallest burst time. Then 7 plus 2, 9. 7 plus 2, 9. So now P3 also completed. Who are left in the ready queue? P2 and P5. P2 and P5. So P2 is having 4 and P5 is having 3. So which one will get, according to SJF scheduling algorithm, which one will get the CPU? The P5 process will get the CPU because it has the shortest burst time than the P2. Means P5. So 9 plus 3, 12. Right? So the P5 also completed execution, and then who is left in the ready queue? P2 is left in the ready queue. The remaining P2 will be 12 plus 4, 16. Right? So all the processes are completed their execution. Now let us calculate the turnaround time and waiting time for each and every process. So we already know the formula for how to calculate turnaround time. Turnaround time equal to completion time minus arrival time. Right? So now let us see for P1. Right? What is the completion time? 7. P2. What is the completion time? 16. P3. Completion time is 9. P4. Completion time is 6. P5. Completion time is 12. Now, turnaround time is completion time minus arrival time. Completion time minus arrival time. So, here arrival time 31402. So, let me P1, P2, P3, P4, P5. Arrival time is 3140. 31402. Right? So now look at the completion time, turnaround time of the P1 is 7 minus arrival time, 7 minus 3. because this arrival time data has given in your problem itself. In your problem itself. So 7 minus 3 that equal to 4. Now P2. P2 completion time is 16. Arrival time is 1. 16 minus 1, 15. So here if you observe that, here also you can able to observe. So we able to get it. So now look at P3. P3 equal to 9 completion time minus arrival time. 9 minus 4 equal to 5. Now P4. So P4 equal to 6 completion time minus arrival time is 0. 6 minus 0 equal to 6. So P5 arrival completion time equal to 12 minus arrival time equal to 2. 12. So this is the values of turnaround time for different process P1 to P5. Now let us recalculate waiting time. Waiting time of the processes. So what is the formula? We already know this formula. Turnaround time minus burst time. Turnaround time minus burst time. So what is the turnaround time? 4. Right? 4 minus burst time. 1. 4 minus 1. 3. Right? Here let me keep it of burst time also. So it will be easy. 1, 4, 2, 6, 3. 1, 4, 2, 6, 3. So turnaround time minus burst time. 4 minus 1 equal to 3. So even we can see that here for P1, if you observe how much time actually it is waited. Means actually 3 milliseconds. 3 milliseconds it is waited. 4 minus 1 equal to 3. Now, so for P2, turnaround time 15 minus 4. 15 minus 4. Turnaround time minus burst time. 15 minus 4 equal to 11. So now for P3, 5 minus 2, 3. So for P4, 6 minus 6 equal to 0. For P5, 10 minus 3, 7. Now how we are going to calculate average waiting time? 3 plus 11 plus 3 plus 0 plus 7 divided by the number of process 5 equal 24 divided by 5 equal to 4 milliseconds. Now the average turnaround time is 4 plus 15 plus 5 plus 6 plus 10 divided by 5, that equal to 40 divided by 5. So that equal to 8 units. Right? So now we will see the primitive version of the SJF. Primitive version of the shortest job. First, scheduling. So let us see one more example. So the primitive version means that if the process comes with the smallest burst time, then that process will acquire the CPU. It can be preempted while in the execution. Right? So let us see the question. Consider the following set of process with the length of the CPU burst given in milliseconds, and here this is the snapshot. So P1 to P4 process are arrived at different intervals 0, 1, 2, 3, and burst time. P1 burst time is 8, P2 burst time is 4, P3 burst time is 9, and P4 burst time is 5. If the CPU scheduling policy is SJF primitive, calculate the average waiting time and average turnaround time. Let us solve this problem. So now primitive. So at time 0, who are the process in the ready queue? Only one process, P1. So what is the burst time of the P1? 8 milliseconds. So P1 at time 0, P1 will take the CPU for execution. Right? So after that, at time 1, now P2 is also entered into the ready queue. with burst time of 4. So here 1 unit, 1 milli-unit or 1 milliseconds, actually P1 is executing. P1 is executing. So now after 1, P2 also is entered into the ready queue and wants the CPU. So with the preemptive nature, so what actually we have informed? You can, if the other process is coming for execution, if smallest burst time, then it will allow to do the preemption. So P2 is having 4 and here 1 unit already executed, 7. How much left? 7. So who is among of these two processes, who is having the smallest burst time? So P2 is having the smallest burst time. It means that P2 will take the CPU. Now P2 will take the CPU and 1 plus 4. So because it requires 4 units of the time CPU. So till 5 units P2 is executed and P2 complete the execution. Now by this 5, so all processes are arrived in the ready queue. So among this, so if you look at 7, 9, 5. So which is having the smallest burst time? P4 is having the smallest burst time. Now P4 will be take the CPU. 5. P4 will take the CPU. And 5 plus 5, P4 requires 5 units of the time and 5 plus 5, 10. So P4 also finished the execution. P4 also finished the execution. Now who are left in the ready queue? P1 and P3. Who are left in the ready queue? P1 and P3. So here 7, P1's burst time is 7, P3 burst time is 9. Who is smaller? 7 is the smallest. So who will acquire the CPU? P1 will acquire the CPU. So P1 is acquired the CPU. So 10 plus 17 milliseconds, P1 will take the CPU and finish the execution. Now who is left in the still in the ready queue? P3 is only left in the ready queue, which will take 9 units of the time. 17 plus 9 equal to 26. P3 also finished execution. So all the process are completed their execution. Here the main important point is you have to look at what time actually process are arrived. And at each and every moment, we'll check that which process is having the smallest burst time. So that only we have mentioned. When process P2 arrives, the remaining time for P1 is 7. The P2 wants 4. Then among of these 4 and 7, who is smaller? P2's burst time is smaller. Then P2 will get the chance. Right? So when P1 is preempted and P2 is executed. Now let us calculate the waiting time for this problem. So by using of this formula, formula won't come on the fly. Actually, with this we to make the simplified, we are using of this formula. Waiting time equal to, because here if you observe that while in the preemptive nature, sometimes P1 is executing against, after some period of the time P1 is again coming and executing. Right? So waiting time equal to total wait time minus actually before starting, number of milliseconds process executed minus arrival time. Right? So let us we see the waiting time for the P1. Waiting time for P1 at what time it is arrived? 0. So is it initially what is the total actually the P1 able to complete? If you observe here, the waiting time of the P1 is here 10. Already 1 unit of the time already has taken. 10 minus 1 minus arrival time is 0 equal to 9 milliseconds. So total P1 is waiting in a queue is 9 milliseconds only. Right? We already have seen that in the before examples while calculating from the GNAT chart, P1 before this starting time is going to be waiting time. Right? 10 minus 1 minus 0 equal to 9 milliseconds. Waiting time for P2 equal to 1 minus, say P2, you look at here, 1. Right? 1 minus, because 1. Here Arrival time is 1. The number of milliseconds anywhere it is executed, no. Means 0. 1 minus 0 minus 1 equal to 0 milliseconds. Waiting time for P3 equal to 17 minus 0 minus 2 equal to 5 milliseconds. So waiting time for P4 equal to 5 minus P4. 5 minus anywhere is executed? No, 0. 5 minus 0 minus 3 equal to 2 milliseconds. So the average waiting time equal to 9 plus 0 plus 5 plus 2. Sorry, 17 minus 2 equal to 15. 15 plus 2 equal to divided by 4. 26 by 4. That equal to 6.5 milliseconds. Right? This is a way people have to calculate the average waiting time for the SJF scheduling algorithm. Now, let us see the another version. Example 2. This you can take down as a homework, or you just the same problem and calculate the average waiting time and turnaround time with SJF primitive version. So, SJF primitive version we are going to call it as again shortest remaining time first scheduling algorithm. So, now we will discuss what are the different problems are associated with the SJF scheduling. The main problem is knowing the length of next CPU request. Knowing the length of the next means that a process next CPU burst is very difficult. Predicting the CPU burst of the next process is very difficult. So, although this algorithm is optimal, but it cannot be implemented in short-term CPU scheduling. And here the main problem is don't know the length of the next CPU burst. So, what are the this problem is existing with this SJF. So, is there any approaches to solve this, or to can approximate the value of the next CPU burst for a process? Means we can able to predict the length of the next CPU burst. That we will see in the later by using some problems like simple averaging and exponential averaging. We will we will predict not exactly accurately we can calculate the length of the CPU burst of a process, but we can use with the formulas we can able to predict, right? See, suppose if the same process and this many units executing, so we can able to predict, right, how much actually the next process will take for the same kind of the work. Like that actually we can predict the next CPU burst. So, this is the formula by using exponential average of the measured length. So, the next CPU burst is predicted as exponential average of the measured length of the previous CPU burst. Previous CPU burst. Okay, I have a process. For this task, I am going to take 20 milliseconds of the CPU time. Then, if another process comes for the same kind of the task, so it is also is using of, we can estimate, right, the 20 milliseconds only will take the T1 also. Like that. So, here we are making generalized formula for this. Let Tn be the actual length of the nth CPU burst. Because nth CPU burst we know. So, the tau n plus 1, the predicted tau, because we are using tau is for predicted. Tau n plus 1 is a predicted value for the next CPU burst, and the alpha value will be ranged from the 0 less than or equal to 0 to 1. So, this is the formula tau n plus 1 equal to alpha into Tn plus 1 minus alpha into tau n, right? This is a formula we will use it for the predicting the next length of the next CPU burst. Now, let us see the advantages of the SJF. With the examples, with the above examples, we will come to know SJF has given the better average waiting time. That's why we are saying that SJF is the optimal, right? So it is better than first come, first serve scheduling algorithm, right? And SJF is also generally used for long-term scheduling. It is not going to use for short-term scheduling. It is because for the batch systems only, this SJF algorithm is best suited, because there in that batch systems, we will come to know the CPU time, CPU burst time. So it is suitable for the jobs running in batch systems, where runtimes are already known. So this SRTF, shortest remaining time first algorithm, is optimal and guarantees the minimum average waiting time, right? We have seen with the examples. Let us see the disadvantages of the shortest job first scheduling algorithm. So it cannot be practically implemented because burst time of process are not known in advance, So this scheduling algorithm may also lead to the starvation. Starvation means that the longest burst time process will wait longer time in the ready queue, because the shortest process keep on coming in the ready queue. Those process will get the CPU and make the long process is going to be wait a long time in the ready queue. So you may have seen the same problem is existed with the FCFS scheduling algorithm. There we have used the word convoy effect. So in the convoy effect also is the same. So there actually based on the order, actually if the shortest process is the same, here shortest process, a process with the shortest burst times is coming into the ready queue, will keep on get the CPU and make the longest burst time process is going to wait longer time in the ready queue. That means that is nothing but starvation, right? So with largest burst time, here priorities I can't able to assign. Priorities I can't able to set for the processes. Processes with largest burst time have poor response time. Obviously, right? Shortest time process means that a process which is having shortest burst times is nothing but shortest process. So those will keep on get the CPU in this scheduling algorithm. Now how we are going to implement of this SJF algorithm. So this SJF algorithm, for this we are going to use heap data structure will be very best helpful. In this min heap is a suitable data structure where root element contains the process with least burst time. So in min heap, each process will be added and deleted exactly once. So with that, what is the time complexity? You may have studied this heap data structure in data structures. So for insertion and deletion, how much time actually it will be taken? Log n time, right? Log n time will be taken to do the operation of either of the insertion or deletion of the time. So thus for n processes, the time complexity is n into 2 log n equal to n log n. The time complexity of the adding and deleting the elements in heap data structure n log n. So these are the references I have used. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.